Hi everyone, my name is Stephanie Olson and I'm an assistant professor of planetary science at Purdue University. Today I'm going to be talking about an aspect of the climate system that does not get a lot of attention, but I think should. Uh, Whereas we're really comfortable thinking about how atmospheric composition can impact climate, um, much fewer people are thinking about how ocean composition, and in particular the salt content of seawater, may influence climate as well. So the suggestion that salinity might impact climate might seem odd, but there are actually several relatively simple reasons to expect a salinity climate relationship. The first is that salt directly impacts the density of seawater. And at the same time, it actually changes the relationship between temperature and density. So fresh water is most dense at 4 degrees Celsius, but salty water is most dense at lower and lower temperatures as salinity increases. And so in combination, these two effects can have a big impact on the density structure of the ocean, its circulation, and ultimately ocean heat transport and climate. And then finally, salt depresses the freezing point of seawater, and that's an effect that may directly limit sea ice formation. And so these effects could conspire to actually have a big impact on climate, particularly within the context of the ice albedo feedback. So as an illustrative example, I would like to first turn to Archean Earth about 2.7 billion years ago. This is an interval of Earth's history where the Earth was receiving far less energy from the sun, and yet we know that there was a liquid water ocean at our planet's surface that was hosting a thriving marine biosphere that was actively influencing its environment. And so reconciling this apparent conflict between reduced solar luminosity and the persistence of liquid water is most typically attributed to higher levels of greenhouse gases like CO2 and methane. And I think that's almost certainly true, but there's potentially a role for salinity as well. So here I'm showing 3 different Archean simulations using Rocky 3D. They are identical except that they differ in the salinity of their ocean. And so you can see that increasing salinity to 50 PSU, which is modestly higher than today, and within the range of theoretical estimates for Archean salinity, ice goes away. And Rocky 3D is actually predicting a climate that is warmer than present day Earth, despite the fact that solar luminosity was considerably less. And so these salinity effects can, in some circumstances, be very important. So in the spirit of this meeting, I have 2 big questions. The first is, can these salinity effects be represented in models that do not include dynamic oceans? Or if we want to model the climates of potentially habitable exoplanets, is it actually very important to include dynamic oceans and uncertainties associated with salinity? The answer to this question is really going to depend on the mechanism that is really driving the climate response. If the primary mechanism by which salinity is influencing climate is related to freezing point depression, then that's an effect that we can actually represent without investing time and computational resources in including oceans. But if it turns out that ocean dynamics are really driving the climate response to salinity, well, then it's going to be really difficult to represent them without including dynamic oceans. The second question I have is, how might these salinity climate relationships play out differently on synchronously rotating planets such as TRAPPIST-1e. So just to set up what I'm going to do, I'm going to compare several Rocky 3D simulations to ExoCam simulations. And in all cases, these are going to be equivalently configured simulations with the notable difference that ExoCam does not include a dynamic ocean. But we have accounted for freezing point depression corresponding to a particular salinity assumed in Rocky 3D. So as a reminder, these are our key and climate scenarios that I simulated using Rocky 3D. And if we reproduce those experiments in ExoCam, this is what happens. You can see that in the experiments towards the left, that the areal extent of full-on ice cover is actually quite similar. But whereas Rocky 3D maintains an open water belt at low latitudes, ExoCam has more of a slushy situation going on, and its ice cover is subject to a stronger seasonal cycle than we saw in Rocky. But if you go up to higher salinity, the two models become really quite dramatically divergent. Where Rocky 3D is predicting an ice-free paradise, ExoCam is actually predicting a snowball Earth. So in terms of model intercomparison, these are as different as two models can get here. I haven't fully sorted out the reasons why ExoCam is giving such an unintuitive result. But I think what this is telling us is that ocean dynamics are playing a really important role in the climate response we see in Rocky 3D. And so to return to the first question that I posed, can we represent these effects without using computationally expensive dynamic oceans? I think the answer is pretty clearly no, we cannot. All right, now on to tidally locked planets. Again, here I am showing 3 Rocky 3D simulations that differ only with respect to the salinity of their oceans, increasing from left to right. This is a TRAPPIST-1e-like planet, except that I'll note that I changed the rotation rate a bit. And what we see here is that, like the early Earth scenario, ice cover decreases with increasing salinity. But unlike the early Earth scenario, this decrease is actually gradual and continuous rather than abrupt. And that's something that actually makes sense in the context of the ice albedo feedback. So Earth's climate system is characterized by bifurcations and hysteresis due to the ice albedo feedback, which produces distinct climate states and abrupt transitions between those climate states. But the ice albedo feedback is actually weakened on synchronously rotating planets, and in particular M-star planets, to the point that these bifurcations and hysteresis disappear. And we actually expect M-star planets to continuously glaciate and then smoothly deglaciate along the exact same trajectory. And so I think that the climate response to varying salinity being smoother makes a lot of sense, actually. Okay, now finally, here are the corresponding ExoCam simulations. And I think the most notable thing here is that the magnitude of the salinity effect is severely muted. But if you squint, you might be able to tell that the trend is at least in the right direction this time. The higher salinity scenarios have a little bit less ice. Okay, so just to summarize and wrap up here, hopefully I have convinced you that ocean salinity can play a really important role in planetary climate. These effects are particularly important on rapidly rotating Earth-like planets, but I wouldn't say they're negligible on M-star planets. And in both cases, these effects really cannot be accounted for without including a dynamic ocean. And so although it adds considerable computational expense, I think it's important that we uh, strive to include oceans um, as we move forward. Thank you for your attention.